Hi guys, Ms. Marusik here, and in this video we're going to talk about the effect that pH can have on solubility. Now, in our previous video on the common ion effect, we talked about how if I have a substance that I put into another substance that's at equilibrium, if the two substances share an ion in common, that can affect the equilibrium system and cause a decrease to the amount of solubility of our substance at equilibrium. And we said that only works if they have that ion in common. Well, that's true most of the time. There is one exception to that, and that would be if I have a equilibrium situation that involves adding or removing an acid or base. I totally change the game when acids and bases are involved. So we're going to talk about two scenarios today that could play out. The first of those is if I have an acid or base that's currently at equilibrium and I change the pH to it, what would that do to the solubility level of that acid or base? Now, this only will affect weak acids and bases because only weak acids and bases can make equilibrium. I wouldn't see the same effect on a strong acid or base because they dissociate 100% and don't make equilibrium solutions. However, the only way to figure out if an acid or base is weak is to first see whether or not it's on the strong list. So as a reminder of our strong list, our strong acids include hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, technically only the first hydrogen coming off of it, chloric, and perchloric acid. Our strong bases include group 1 and 2 hydroxides except Be and Mg. If an acid or base is not on that list, then that means I could have a weak acid or base that would have equilibrium, that I could change the solubility of that solution. Now, there's some different ways that we can word the shift that would occur to that acid or base equilibrium system. We could say that, hey, what if I add this strong acid or base into it? Or, hey, what if I add H plus or OH ions into this solution? Or, hey, what if I decrease or increase the pH of that solution? What's interesting is even though all of those statements I just said use different words, they actually all were the same exact kind of processes, okay? So to kind of remind ourselves of the kind of tie between all those statements I just said, we need to, for just a moment, review a little bit about pH. Increasing the pH is the same thing as making a solution more basic. As a reminder, a base has a pH somewhere between 7 and 14, which is the same thing as increasing the hydroxide ion concentration of that solution. Decreasing the pH is the same thing as making a solution more acidic. Remember, acids have pH somewhere between 0 and 7, so on the low end of the spectrum. And that would be the same thing as increasing the H plus or hydrogen ion concentration of the solution. By the way, another way that you could word hydrogen ion concentration is hydronium ion concentration. H3O plus 1. It shows exactly the same thing, except there I'm showing it attached to water. So same exact thing. So here's the deal. Let's say I have a weak system where I add in the same ion that's present. Like I have a weak acid and I add an H+. Obviously, that would be the common ion effect playing out, and so I could figure out how my equilibrium would shift accordingly. Or if I had a weak base and I add in an OH, I could figure out how it shifted accordingly to the common ion effect. However, I can also add in the opposite ion into the solution and still see an effect. The issue with H and OH is that they will interact with each other and form water. They'll neutralize each other out. And so that can end up pulling that ion out of the solution. For example, if I had a weak acid where I had H plus and I added in OH to that solution, the H and the OH would react to make water, and effectively what I've done there is I've reduced the amount of hydrogen ion in the solution. So let's see some examples where this plays out. So the first example says, hey, would the solubility of nitrous acid increase or decrease when sodium hydroxide is added to the solution? So the first thing I'm going to do is I'm going to kind of evaluate what kind of substances I have here. Nitrous acid, I don't see that on my strong list of acids, and so therefore I can assume that this is a weak acid. This guy has hydroxide, which I recognize as being something that we typically see in bases. And I also see that it has a group 1 ion with it. So therefore, I know that this is a strong base. So I want to figure out, would the solubility of the nitrous acid be affected, and how, if I add this strong base into it? Well, let's first talk about what that strong base would do in the solution, okay? If I have my NaOH, which, by the way, I don't know what state for sure it starts off at. I don't know if it's a solution to begin with that's dissociating ions, or if we have a solid that we're putting into water. I'm going to put solid here because most of the time hydroxides are solids at room conditions until I put them into water. But I'm going to put a one-way arrow here for its dissociation because, again, it was strong. And we're going to dissociate that into sodium ions and hydroxide ions. Okay, so now I'm going to do the same thing for the nitrous acid. So we're going to have HNO2. Now, acids tend to start off even as AQ before I dissociate them, but I'll be honest, the state here is not really going to matter since I'm not writing an equilibrium expression for this. But what does make a difference is that I'm going to put a two-way arrow here because it was weak. We can make an equilibrium. And so we'll end up with hydrogen ions and the NO2 ions, the nitrite ions. All right, now upon first glance, it doesn't look like there's anything in common between these two reactions where one would affect the other. And you'd be right, they don't have anything in common, but that doesn't mean they don't affect each other. If you notice, here we had hydrogen, but on this other equation we had hydroxide. And unfortunately, what will happen is the hydrogen ions and the hydroxide ions will react to make water. Now you also notice I put a one-way arrow with that. That's because that neutralization is very driven toward the product side, very driven toward the water. So essentially what I'm doing is I'm continually pulling out hydrogen ions to react them with those hydroxide ions to make water until one or the other runs out. So I'm constantly reducing those hydrogen ions. Now, what I'm going to do is I'm going to reason this out from kind of a standpoint of using Le Chatelier's principle, where this would end up changing my value of Q, and what would equilibrium need to do to get Q to be equal to K again. So to kind of talk through this process, again, what I'm doing here is when the H from the nitrous and the OH from the sodium hydroxide are interacting and making water, what I'm effectively doing is reducing my hydrogen ion concentration. Now, because I'm doing that, I'm effectively removing a product which will cause my Q to decrease. Now, what that will cause is the Q to be less than the K, which is obviously a problem because now we're not at equilibrium anymore. At equilibrium, those two should be equal to each other, but now the Q is too small. So to increase the Q, I'm going to need to shift this equilibrium. Now remember, I'm removing H plus 1. I always shift towards the side that I removed from in order to replace it. So to increase Q, I really want to shift to the products. Meaning products would increase and reactant would decrease. Now, let's think about what that's doing to solubility. Solubility is the amount of this guy here, this HNO2, that is splitting up into ions. How much of this are we losing? Well, if more and more of this is getting shifted to that product side, that means more and more of this is dissociating. More and more of it is dissolving in the solution. So what that means is that the solubility of the HNO2 will increase constantly until either the hydrogen or the hydroxide runs out. Like one of them is going to run out, and then at some point it'll reach equilibrium again, but it's going to continually fight to get to that equilibrium until something runs out. Okay. All right, so let's look at another one here. This one words it a little bit differently than our previous one. The previous one talked about adding in a base. Here we're talking about instead changing pH. So this one asks, hey, what would happen to the solubility of silver hydroxide in each of the following scenarios? So this first one here, as I said, mentions that the pH is being increased. Now let's think about that for just a moment. If the pH is being increased, what that means is that we're becoming more basic. And if I'm becoming more basic, that's the same thing as increasing the hydroxide ion concentration. I'm adding in OH into this, okay? So it's the same thing as saying, hey, I'm adding in a strong base. It's just they worded it a little bit different here, okay? So now we have our AgOH solution, which I know that Ag is not on the strong list. It's not group 1 or 2 hydroxide. So therefore, I know this is weak. Also being a hydroxide is probably a solid at room conditions. I'm going to put a two-way arrow because we said it's weak. And we're going to have Ag plus 1 ions and OH negative 1 ions. Now, we see here on this one that, hey, I'm adding in hydroxide, but I have hydroxide ions present. So this is one of those situations where it is a common ion effect. I'm adding in more of that OH. Okay, so even though this is a common ion effect, let's still talk through the same explanation that I would use for Le Chatelier's principle. This would be what you would want to kind of talk through, say, on an FRQ question. Okay, so if I'm adding in that hydroxide concentration, that means our OH concentration is increasing, which since I'm increasing a product, now what's going to happen is Q is going to increase. So that causes the Q to be larger than the K, which again is an issue because at equilibrium, I want those two things to be equal to each other. So to decrease the Q and get it back to equaling K, this would cause us to shift to the reactants. As a reminder of Le Chatelier's, I always shift away from what I add. If I'm adding the OH, I would want to shift back to the reactant side. Okay, so a shifting to the reactants means that less of these ions are going to be formed and more of that solid is going to be stuck together. So what that means here is that the solubility of the AgOH has decreased, which, by the way, if you remember anything from our discussion about the common ion effect, we said that when I introduce a common ion into a solution, that the solubility level would decrease, and that backs this up completely. So just kind of the way you would want to describe it with Q and K here, if you had to do that in an FRQ question. All right, let's look at the next example that has to kind of do with this same one here. Here it says, hey, what if the pH of the AgOH solution is decreased? So we're kind of dealing with that same process, except now we're doing the opposite effect to it, okay? So to start us off here, pH being decreased means that I'm changing this to be more acidic. And if I'm changing it to be more acidic, then what that means is I'm increasing the H plus ion concentration in the solution, okay? So I'm going to rewrite here my equilibrium system. Our AgOH solid, two-way arrow, silver ions, and hydroxide ions. And at first glance, we're like, I don't have an ion in common, but then I'm like, oh, wait a minute. What do we know about H and OH? Well, we know that those two are going to interact with each other. And when they do so, the H and the OH end up creating water, which again, as we know, is very driven toward that product side. So again, effectively what we're doing here is we're removing OH constantly out of the solution. So to kind of, give our explanation to this, and again using Le Chatelier's principle, as the H and the OH interact to make water, what we're effectively doing is we are decreasing our OH concentration. So what happens is as I'm removing a product, our Q value decreases. This causes Q to be less than K. Okay, so that means that we're going to need to figure out some way to increase the Q, which again, to increase Q, we would want to shift to the products. Okay, which makes sense because again, if I'm removing something, I shift towards what I removed to replace it. But what that means is that more and more of this AgOH is becoming ions. Okay, so again, more and more of it is dissolving. So the solubility of the AgOH is increasing. More and more of it is dissolving to become ions. All right, let's look at another kind of scenario here that we could have. So far what we've looked at is if I have a weak acid or base, what would happen if I change the pH of that solution. But I could also technically have some sort of salt that I add an acid to, that because I could potentially form a weak acid from that combination, I could end up pulling an ion out of the solution. So again, kind of another weird situation that we could have if an acid or base is involved. So to kind of see how this works, let's go ahead and jump into an example, and I'll kind of talk through some of this stuff at the top here as we go through. This first one here says, would the solubility of calcium fluoride increase or decrease when hydrochloric acid is added to the solution? So to kind of evaluate what I have here, calcium fluoride, if they're asking me about the solubility of it, that means that it must be one of those insoluble ionics that can dissolve a little bit, and so it's making equilibrium. I notice hydrochloric acid is on the strong list, so that's a strong acid. So what I'm going to do first is, just like kind of we did before, I'm going to write my equation for the hydrochloric acid dissociating. And because it's strong, I'm going to put a one-way arrow. So again, all of this hydrochloric is going to split into these ions. But then I'm also going to have the calcium fluoride, the CaF2. And that's starting off as a solid. I'm going to put a two-way arrow because, again, it's one of those insoluble salts that I can affect the solubility of. I'm going to have calcium plus 2 ions and 2 fluoride -1 ions. Now, again, upon first glance, you're like, okay, these have nothing in common with each other. So this is not a common ion effect situation, which you would be correct, except that I noticed that one of the substances is an acid. And I'll always want to be careful with equilibriums and these acid problems. The issue is that this hydrogen and these fluorides can interact. And when they do so, what happens is the hydrogen plus 1, and actually only one of the fluoride ions would end up making an equilibrium between the weak acid hydrofluoric. Now, this being a weak acid that I'm forming means that this is very driven towards the hydrofluoric, that very little of it is going to stay split up into ions. So just like before, what we're effectively doing here is constantly removing those fluoride ions to create the hydrofluoric acid. And so that's going to create a shift to our equilibrium. So just like before, what we're effectively doing here is the fluoride ion concentration is constantly being reduced. And since that's a product, the Q is going to be constantly decreasing. So again, this causes the Q to be less than the K. So in order to increase Q back to where they equal the K, I would need to shift to the products. Which again should make sense because we know we shift towards what we remove to replace it. So if I'm constantly removing the fluoride, I'm going to be shifting to that product side. However, if I'm shifting to that product side and constantly making ions, essentially until the hydrogen runs out, if I'm constantly shifting to that side, then that means I'm constantly dissolving the calcium fluoride. So what I'm doing is I'm taking the solubility of the CaF2 and I'm increasing it. It's constantly going to be dissolving more and more to get to that product side. Now, I'm going to show you one other one that's similar to this, but it's got kind of another little, I don't know, quirk to it, if you will, I guess. So on this one, we kind of start off the same way. It's asking about what is the effect of solubility on lead to carbonate, except they word this one a little bit different. Instead of saying, hey, I'm adding in a strong acid, here they're just saying, hey, I'm decreasing pH by adding in H+1 ions. So same idea, I'm increasing that number of H+1 ions in this solution, even though the H+1 ions aren't in the lead to carbonate. So what I'm going to start off by doing is writing my dissociation for the PbCO3, which since it's talking about solubility, it must be one of those ones that make equilibrium. I'm going to have lead and my carbonate here. And then I'm like, okay, well, at first glance, hydrogen, it's not in there. So is there anything in common? Well, there's not, but the hydrogen and the carbonate could interact. And when they do so, something really interesting happens with this one. First off, the hydrogen, and actually would take two of them, interact with the carbonate and form an equilibrium with H2CO3 carbonic acid. However, we can even take this a step further. Carbonic acid is notorious for decomposing even further. Carbonic acid will decompose into water and carbon dioxide. Oop, I put gas there, I should have put liquid there. Sorry, that's a liquid. Okay, so what's happening is that not only am I driving this toward the weak acid, but then when the weak acid decomposes, it's constantly pulling that equilibrium further and further along to these substances that are being released and can't go back to the original substances. So we are very much driving this toward the product. Now, the net effect of this is the same thing we saw up above. What's happening is our carbonate concentration is constantly being decreased, which, let's be real here, if our product is decreasing, the Q gets lowered, causes Q to be less than K. So in order to increase the Q, we would constantly be shifting to the products. So I'm constantly shifting toward these ions in order to replace the carbonate that's being lost. And the net effect is that this lead carbonate over here is constantly going to ions. And so the solubility of it is constantly increasing. I'm constantly dissolving more and more of it going to that product side. All right, guys, hope this helps. If you have any questions or comments, please feel free to email me. Bye, guys.